Hey y'all, Dr. G here. In this video, we're going to continue our discussion about nucleic acids. And we're going to focus on how we can take our building block, NTP, so triphosphates, and convert them into long polymers of DNA or RNA. As a quick review, in the first video of this series, we talked about the overall kind of base structure of these nucleic acids, and how there are three key regions. The central sugar, which is either ribose or deoxyribose. Attached to this central sugar through the first carbon, 1' carbon, is a nitrogenous base, and attached to the 5' carbon is one or more phosphates. We then further explored the structure of the bases, right? And we talked about how all of the nucleic acid bases are grouped into two categories, either purines, the two-membered rings, or pyrimidines, the one-membered ring. And we talked about some common themes that I think is really helpful to help you recognize and draw these structures, focusing in on the repeating pattern of nitrogen, carbon, nitrogen, focusing in on the hydrogen bonding pattern needed for Watson and Crick base pairing, focusing in on making sure that all of the atoms have an octet. Okay? In this video, we're going to focus in on the chemistry that has to happen in nucleic acids to create nucleic acid polymers. So just like amino acids, the idea is we have our building blocks, and those building blocks can condense together to make polymers. In this case, the way that it works out is in many ways really, really similar. We have a reactive primary alcohol. We're going to see that this is the 3' hydroxyl group. And then we have an electrophilic phosphorus. So this is different than amino acids, which had an electrophilic carbonyl, but the chemistry is going to be really, really similar. We can think about this being initiated by deprotonating this hydroxyl group, okay, or weakening this bond. So a base initiates this reaction by deprotonating the alcohol. Okay, this gives us kind of an intermediate, which you could choose to ignore if you'd like to, but just generally speaking, this is making it a better nucleophile, which can then attack this central phosphorus, which is really electrophilic. The electrons flow up to the oxygen to give us an intermediate. This intermediate is a 5-coordinate phosphorus. Let me go ahead and draw it all out here. All right, so this 5-coordinate phosphorus with the new bond with this primary alcohol. Okay? Once we have this intermediate, the idea is it collapses. We reform the double bond, reform that pi bond, and one of the bonds that was originally attached to the phosphorus is released. So in this case, let's just think about releasing the OX, but we could also release the OR prime. Okay, and eventually, so after this chemistry is done, we end up with our phosphate that now is attached to our alcohol. Okay, things to recognize here that I'd like to point out is that this is called a phosphodiester bond. Okay, remember an ester looks like this. So it is a carbonyl attached to an oxygen, and each of those atoms are then attached to another carbon. So this is an ester. A phosphoester would be a phosphorus replacing this carbon. And a phosphodiester is having a phosphoester in two directions. So I have a phosphoester here, and I have a phosphoester in this direction. So I have a phosphodiester. This is the linkage that links together DNA monomers in polymers of DNA. The other thing I want you to notice is that all of these phosphodiester bonds have a negative oxygen on the phosphorus. So we end up with a polyanion present on the backbone of DNA and RNA. Okay, so let's see this in action in the actual structure of DNA and RNA. So I'm showing two nucleotide triphosphates. Okay, I'm highlighting the 3' carbon of one of them and the 5' carbon of another. So the idea is that we have some base that can deprotonate this 3' hydroxyl group. I won't bother drawing intermediates this time, but I will draw them in different colors. Okay, so that deprotonation happens, making the oxygen more nucleophilic. The oxygen can then attack the electrophilic phosphorus. Electrons flow up to give us our next intermediate. And then that intermediate can collapse, and the bond that's going to break is between the phosphorus and the other two phosphates. So this molecule, which is represented by two P's here, which each of these P's represent a phosphate group. So this collectively is released as diphosphate, or sometimes we see it abbreviated PPI or pyrophosphate. Okay, so this is one of the products, and the other product is a new bond between the nucleotide triphosphate we have in white here it's shown as an H, so this is DNA. We have our oxygen, and now this is attached to the phosphorus, which is then attached to another nucleotide. Okay, so here is our product. Things to point out. Here is our phosphodiester linkage. Right, so we have this phosphodiester linkage as we're expecting. The first nucleotide that's attached here still has a triphosphate on the 5' carbon. So here's our 5' carbon. So this now dimer of nucleic acids still has a 5' triphosphate. Additionally, and very importantly, it has a 3' hydroxyl group. So this 3' hydroxyl group could then serve as a nucleophile to initiate another attack onto another nucleic acid. So we have a reactive 3' hydroxyl group that can serve as a nucleophile to then continue the polymerization process, ultimately resulting in long polymers of DNA where each of the nucleic acids are linked together by a phosphodiester bond. The 5' end is marked by a triphosphate. The 3' end is marked by a free 3' hydroxyl. Okay, in the next video, we'll start thinking about how these DNA and RNA polymers can come together to make the structures of DNA that we have probably seen before, our double helix.